Hello.
Hi.
Would you like to introduce yourself?
Yeah, my name is Jacob Haimes.
Okay, let's talk about your research. What are you presenting at NeurIPS?
So the paper is about noise injection to elicit sandbagging behavior. So the idea is either intentionally or through the training process, a model might underperform on a benchmark intentionally, either because the developers are gaming the system, which we've seen in cases like the Volkswagen emission scandal in 2015-ish, where Volkswagen had a system that they incorporated into their car, which made it, when you were in the evaluation environment for emissions, it produced a different emission output. It was lower than what the actual reality was when it was used on the road. So that is an example of gaming the evaluation. If there are regulations or things that are using benchmark scores as a means to say you shouldn't or should deploy this or can't use this in certain ways, things like that, then there is the financial incentive there for a company to intentionally underperform on that evaluation in that evaluation setting, or overperform when they otherwise wouldn't. Given that, and then also there are concerns, like from some of my co-authors especially, of like, what if the systems are doing that sort of, it's a learned behavior in the training process, so the developers aren't even trying to incentivize that, but that's just part of what's happened due to the training process. And if that is the case, then we would be using these benchmarks and these other evaluations, and they would be very wrong, right? Because we wouldn't actually be measuring the true capability. We would be measuring what was being displayed as the capability. And so if that is the case, we should be able to elicit that and know when that's happening. And we use a method of putting noise, so just Gaussian noise, into model weights. Mm-hmm. And by doing that, an analogy is like kind of makes the model drunk, so to speak. Mm-hmm. Fuzzes things up and starts to make things more incoherent until you get to a point where there's just like complete failure of the system. It can't accurately respond to any inputs. But on the way, for sandbagging models, what we see is an increase in performance. When you add noise, the performance on the benchmark goes up before it goes down. And that does not happen in a meaningful way for not sandbagging models. There might be like a 0.01 or something % increase that's just like randomness. But in the sandbagging case, you see an improvement of at least 1.3, usually more, in some cases like much more, in this improvement ratio. So as you increase the Gaussian noise, the improvement goes up substantially. That shouldn't happen. And so if that occurs, to be, at the very least, very suspicious of sandbagging and to look into it further. But, all of the cases that we tried across all sandbagging and models of various different types across different evaluations. So we used GSM 8K. We also did various multiple choice evaluations. And across every single environment that we tested against, our system or our method reliably shows that improvement ratio is significantly greater than 1. And so we can identify when that's happening.
So what is your concern when the base model weights are not performing to the same degree as the noised ones?
What that implies is that for some reason, it is intentionally underperforming on that evaluation question. It could do better.
So is this related to the kind of work on models intentionally underperforming in like reasoning models so that they are not revealing their true ability?
Yes. So that's sort of what I was alluding to earlier with deception. The idea that maybe a model has learned to try to deceive the user, and so it is pretending to be less capable than it actually is, because then it will get deployed and then etc. So that is a concern.
Do you think that deception on evals translates to deceptive behavior more broadly in conversations?
No, I don't think it necessarily does. I think there's possibility that happens. And thinking about it, if you're intentionally training any sort of deceptive behavior into a system, it's probably more likely to see it in other areas as well. Even if you're unintentionally training that sort of behavior into the system, it's probably more likely to go to other areas. But I would not say by default that it translates across like different domains.
What makes your approach special compared to other work that's been done on deceptive behavior?
Yeah, so the baseline sort of, that we compare to is other ways to detect deception. One way is to use labeled data sets. To do that, you need labeled data sets, right? So you need to have, like, this is the correct, this is the not correct of the problem that we're looking at. But that takes a lot of resources to create. And you also need more access to the model weights than what you need with our approach, which we call gray box is what you need, because you just need to be able to know that you're adding noise to the weights. You don't need to know what the default value is.
What sorts of models does that unlock for you?
Well, so that doesn't actually, in practice, unlock anything for us. But let's say a government had privileged access through an API. Like, this was something you'd have to set up. But my thought process, at least, is it's a much easier ask to say, can you give a third party access to adjust the model weights, but not know what they are? Like, a company is more likely to say yes to that than they are to just give over all of the weights to that third party, I think.
Do you and your collaborators have follow-up work in the already cooking, or?
Yeah. So actually, Cam Tice, who's the lead author, is working on chain of thought reasoning monitoring, and has founded a group called Geodesic Research. And so he's definitely working on stuff there. I know that there's also been a related work that was about adding noise in the prompt space, and then also adding noise in the latent space. So we went right for the weights, but you can apply this at different stages, and the behavior is similar. It's not the exact same, but you still see this increase, which shouldn't happen to that extent, at least. And so that's, I think, a very reliable thing, and is another tool in our toolkit for understanding these models and being able to have robust, effective evaluations where we can, at the very least, know if we shouldn't be trusting them, but ideally, improve that information as well.
Very quickly then, what is the direction that you're most excited for, or what is the outcome that you're most excited for in this research direction?
I think the part that I'm most excited for with this particular one is that it's something that is immediately implementable with low cost to the frontier, models or whatever you want to call it. You can do this now with benchmarks. It makes the results more reliable, and it's easy to do. And so, we can do it. It just makes things safer immediately, and I think, that's great.
Yeah, it sounds really interesting. Well, thank you for taking the time to chat with us about your work.
Yeah, thank you so much. I really appreciate it.